Hi guys, good morning. It's another lovely Wednesday. I hope we're all doing fine. Hope your week has been great. Okay, now today we're having further mathematics, so we're going to be looking at a new topic. Actually, the second part of the topic we were discussing previously. But before that, I want us to look at a trick that is very interesting, and we're going to it's going to be applicable for questions we need to solve. Okay, so let's look at the name of the trick is not necessarily something that you've not heard of before, but it just involves subtracting a number from 1000. How do you do it quickly? How do you do it as fast as possible? So subtracting from 1000. Now, for example, I'll give you an example of a digit, but let me just give you an arbitrary one. For example, you have maybe 275 from 1000 and you want to do it in your head and quickly. How do you do it? So first of all, what you need to know is you just need to simply subtract all the digits except the last one from 9. So you're going to subtract all the digits except the last digit from 9. Okay, let's try that out with another example. So look at this: 1000 minus 725. Okay, so based on our explanation, what we just need to do here is 9 minus 7, 9 minus 2, and then for the last digit 10 minus 5. So this is easier to do in your head. 9 minus 7, 2. Oh, 9 minus 2, 7. Oh, 10 minus 5, 5. Yeah. And then you combine everything together, so you would then have 275. Okay, so try this out when you have a digit to subtract from 100, or a number to subtract from 1000 rather. You can also apply the same from 100 anyway. You just have 9 minus the first digit and 10 minus the second one. Yeah, you can also apply that. Now let's try something bigger, subtracting from 10,000 now, no 1000 again, subtracting from 10,000. So you have a big number you want to subtract from 10,000. So what do? You do the same thing. You subtract all the digits except the last one from 9. So you would have 10,000 minus 6,217, for example. You would say 9 minus 6, 9 minus 2, and 9 minus 1. Then you do 10 minus 7. So 9 minus 6, 3, 9 minus 2, 7, yeah, 9 minus 1, 8, and 10 minus 7, 3. Wow. Easier in your head than, trying to use a paper and a pen to work it out, okay? So this should give us 3,783, okay? Then, what about a scenario where you want to subtract a number from 10,000, for example, but it's not a 4-digit number? It's not a 4-digit number. What do? Now you still maintain the same thing. Subtract all the digits except the last one from 9, but you must reserve one nine, because it's not a 4-digit number. It's less than the usual, so you must reserve 19 that you are not subtracting any digit from, since you don't have any digit to subtract from that 9. You just reserve the 9 where as it is. So you should have something like this. For example, 10,000 minus 884, you would reserve 19, then you do 9 minus 8, 9 minus 8, and 10 minus 4. So by the time you bring that all together, you would have 9,116. Okay, so now I have always said this and I would always say it. Mental matrix are not things that are compulsory for each and every person, based on your, everybody thinks in different ways, right? We all have differences in our cognitive abilities, right? Yeah, so everybody has their way of also processing mathematics. So when you see a trick that you love, that you can work with, you pick it. If you do not like it, if something that is difficult for you to understand, then you shouldn't struggle to understand it. It's just a trick. It's not something that somebody else came up with, so you can come up with yours. Okay, so pick the ones that are easy for you to understand and easy for you to take a look at and run with them. But that doesn't mean that we should just discard everything. Sometimes we can be funny and we just don't want to try. I don't mean that. I mean, try. But when you've tried and you see that, okay, this particular trick isn't working for me, this one works for me better, pick the one that works better for you. That's a good thing with these tricks. Okay, so that's our mental matrix segment for today. We're moving on to our topic for today. So we're talking about partial fractions in the last further mathematics class. We looked at some things. I'm just going to give you a quick recap, but if you have forgotten any of the things that we looked at, you can always run through the video, the former video, previous one again, and come back to this one. Okay, so let's recap. Let's take a quick recap. We talked about how to split compound fractions. We mentioned methods that we can use. We talked about the cover-up method. We talked about the comparing coefficients method. The cover-up method involves substituting values of x that help you to find the unknown values of a, b, and the likes. Okay, while comparing coefficients method means you expand the right hand side, you compare coefficients on the left and on the right together, and you make up equations that you can solve simultaneously to get the unknown values. Okay, so those are the two methods that we discussed, and we also talked about the different types of expressions you could possibly have in the denominators. We said you could have non-repeated linear factors. We said we could have other non-repeated factors that may not be linear, like in terms of quadratic or cubic, polynomials and so on and so forth. So those were the two types of denominators that we discussed. So today we're going to be looking at another set of denominators, expressions we can find in the denominators, and I'll also be introducing a new method for solving in addition to the methods that I have shown you before. So repeated factors in the denominators, that's one thing you can have, and another type of fraction you can have is the improper fraction. So we'll look at how to deal with all these issues. So let's start with the repeated factors. Let's start with repeated linear factors now. What if the repeated factors you have are linear? What do you do? Now, the denominator has a repeated linear factor of the form ax plus b raised to the power n. You assign partial fractions with constant numerators up to the nth value. I will explain what that means. Just follow me now. So we have something like this. For example, 2x plus 3 over x squared into x plus 3 whole square. So we start with x squared. X is just a constant now, but it's repeated, right? It's repeated. So since it is repeated, it's squared, right? We're going to have two partial fractions assigned to just x now, but they will be in ascending order. So the first fraction would have a denominator of x. The second fraction would have a denominator of x squared. That's all. That is all. So you would have a over x plus b over x squared. That deals with x squared as the denominator now. Okay. Now the second part, you look at the next part. You say, okay, x plus 3 is linear. Okay, fine. That's good. Now that means, of course, that our numerators will be constants. That's just a, b, c, whatever letter you like. Now x plus 3 is linear. Okay, and it's repeated. It's squared. So we would also have two fractions for that in ascending order now. So we have c over x plus 3 plus d. When I say ascending order, I mean the powers. You start with the power of 1, that's just x plus 3, then you move to the square, since you have the square there. If it had been cubed, you would have three fractions then. 1 would be raised to the power of 1, that's x plus 3, then you'd have d over x plus 3 square, then you would have e over x plus 3 cubed, if it had been raised to the power of 3. So there's nothing difficult in this if you understand the principles. The major work here that you need to do here is to understand the principles that we use to split these compound fractions. So if you can understand these principles, then you're good to go with any type of fraction that you may find. Okay, let's go to the next one. So when we have repeated factors in the denominator that are not linear now, they're non-linear, what do? Okay, so if the denominator has repeated non-linear factors of the degree n and it's raised to a power of x, assign partial fractions with numerators of the degree n minus 1. We said that previously. Now up to the xth value based on the power it is raised to. Let me show you. Let me break this down so you don't get confused. Look at this example. So for example, we have x squared plus 3x plus 5 over x plus 2 into x squared plus 3 raised to the power 3, right? Now x plus 2 is linear and it's not repeated. So we just assign one partial fraction to that and the numerator should be a constant. So a over x plus 2, that's easy. Okay, then we see x squared plus 3. X squared plus 3 is not linear. It has a power of 2. So our numerators will be linear values now. Okay, and x squared plus 3 is also raised to the power of 3. So we're going to assign three different partial fractions to it, starting with the power of 1. So we have bx plus c, that's our linear numerator, bx plus c over x squared plus 3, that's raised to the power of 1. Then we say dx plus e over x squared plus 3 all square, that's for the second power, that's the second fraction, plus fx plus g over x squared plus 3 raised to the power of 3, that's our third fraction. Okay, so based on the power of the denominators, you would also know how many fractions to split that compound fraction into. Okay, so like I said, try to understand the principles. If you can do that, then you can understand partial fractions. Okay, let's move on. So let's take an example. X squared plus 3x plus 1 over x squared into x plus 3 all square. Okay, this one is easy, so we can split it out. We looked at something like this. We can split this out into a over x plus b over x squared plus c over x plus 3 plus d over x plus 3 all square. Now the denominators here are linear and they are repeated. So you can see for x squared we have 2 fractions. For x plus 3 all square we also have 2 fractions. Now the next thing is to combine the right hand side. You know, this is the denominator is this. Okay, so for a over x, if we do remove x from this denominator, we have x into x plus 3 all square. Okay, then if we remove x squared from this, we have x plus 3 all square here. If we remove x plus 3 from here, we have x squared into x plus 3. And if we remove x plus 3 all square from the denominator, we just have x squared left for d now. Okay, so that's that for combination. Then we pick the numerators of both fractions. That's our premise, that the numerators must be the same. So we pick the numerators and then we form our equation. Now the next thing is, you need to ask yourself, I need to get at least one unknown. Okay, so what do I need to substitute? One unknown at a time anyway. Now the question now is, look at the denominator. The denominator is x plus 3 x squared and x plus 3 all square. So if I substitute 0 into this, into x somewhere here, I know that, okay, into all these equations, I know that some of them will cancel out and I'll be left with something. If I substitute x as minus 3 based on the denominator here as x plus 3, if I substitute x as minus 3, it means some of all these terms will cancel out and I'll be left with one unknown. So you need to think based on the denominators what you would substitute. Okay, so let's start with b. To find b, let's put x as 0. Okay, because we know that if we put x as 0 here, this cancels out. This cancels out because 0 squared is 0, and this also cancels out. So we are left with only b. Can you see the concept now? So we should have 0 squared plus 3 into 0 plus 1, and we put 0 in everything else, and that gives us 1. From this left hand side, 1 equals to 3 plus 0 here is 3. 3 squared is 9. So 1 equals to 9b, and then our b is simply 1 over 9. Okay, so that's great. That's great. Now that's not the end. We're just starting. So let's try to go back to our left equations, the equation that we're able to obtain from our left and our right side. So this is our equation. Let's now put x is minus 3. That will give us d, because if you put x is minus 3 here, this cancels out, this cancels out, this cancels out. So let's do that. So put minus 3 wherever you see x, and then you get something that looks like this. This gives 0, this gives 0, and this gives 0. So the others, minus 3 square is 9. 3 times minus 3 is minus 9. So 9 minus 9 plus 1 gives us, minus 3 square is 9. So 9d. Okay, so 9 minus 9 is 0. So 1 equals to 9d. And d equals 1 over 9. Right? So we've gotten two answers. We said b is 1 over 9 and d is 1 over 9. Now, the next thing is we're going to use what we call the method of direct substitution. And how does the method of direct substitution work? We assume other values for x. We've used 1, 0, and minus 3. So let's use other simple values like 1 and minus 1. Now, when we assume these values for x, we substitute the values of b and d that we have obtained into the equation also. Okay, so we are trying to look for 2 more equations now. So let's do that. Let's substitute x as 1 and also put b and d where they are supposed to be. So you would get something like this. Just try to look through it step by step, you get something like this. And then if we simplify this, you should have 1 square, 1, 3 times 1, 3, 1 here. This gives us 4 square, which is 16a. This gives us 4 square, which is 16 over 9. This gives us 4c, and this gives us 1 over 9. So by the time we try to manipulate this, we should have 5 equals 16a plus 4c plus 17 over 9. Let's take 17 over 9 to 5. So we have, if we rearrange after taking 17 over 9 to this side and we rearrange, we have 16a plus 4c equals 28 over 9. Okay, now we can make that more presentable by multiplying through by 9. Then we can still go for that to divide by 4. Okay, so that gives us 36a plus 9c equals 7, and that's our equation 1. That's our equation 1. So remember that our goal here is to get 2 equations. So let's continue. Now let's use the simplest possible values for x. Take note of that. So let's use x as -1 now. We've used x as 1. Let's use x as -1 now. So how do we do that? We put -1 anywhere we see x. So we should have something that looks like this. You can just go through it and see how, we put -1 into everything. Okay, so when we do that, simplify that, we'll get 1 here, 1 minus 3 plus 1. This gives us 2 square, which is 4 times -1 minus 4a. 2 square, which is 4 plus 4 over 9 here. 2 times 1 here, 2c, and this gives us 1 over 9 here. So we can simplify this and get -1 equals -4a plus 2c plus 5 over 9. Okay, then we can take 5 over 9 to this side, to 1, and then rearrange. So that gives us -4a plus 2c equals -14 over 9. As usual, we can multiply through by 9 to make the equation presentable, and we have -36a plus 18c equals -14. Okay, so that's equation 2. So you can see it might be long. Yes, I agree with you, it's lengthy, but it's not difficult if you understand the principles behind the solution. So the next thing is to bring back the first equation. Remember that this method we just used is called the method of direct substitution. Remember that? So we just need to now bring back equation 1, and then we're good to go with our 2 equations, and we can solve them simultaneously. So we should have something like this. So if we're to solve this simultaneously, let's just add the 2 equations together. So we should have 27c, this cancels out, so 27c equals to -7 here, so c is -7 over 27. Then to get a, let's substitute this c into equation 1. You can use either of the 2, but I decided to use equation 1 because of the minus sign in equation 2 here. So for this now we have 36a plus 9 into -7 over 27 equals 7. If we manipulate there, we have 36a equals to -7 over 3 equals 7. So I think say -7 over 3 equals 7, and then 36a equals 7 plus 7 over 3, and that gives us 28 over 3. So we divide that by 36, and we have a as 7 over 27. So now we have a as 7 over 27, b as 1 over 9, c as -7 over 27, and d as 1 over 9. So we can substitute all those values. This is what we have. Then we can bring down the denominators here down to these positions. So we can bring everything down. 27 goes down, 9 goes down, 27 goes down. Remember that there's a minus here, so it changes this plus sign to minus here. Okay, so we have this as our final answer. Yeah, so that's our answer. Those are the partial fractions. Okay, those are the partial fractions. Okay, let's move on to something else. Okay, so we're going to improper fractions now. Now, based on our knowledge of improper fractions, we know that it means the numerator is higher than the denominator. There's only a slight difference here. Now, for our fraction to be improper in this case, the numerator is either of a higher degree or of an equal degree to the denominator. So if the degree of the numerator is higher or equal to that of the denominator, then it's improper. And then you need to use the long division method to simplify before you can split into partial fractions. Okay? So let's do that. So examples of improper fractions. Now look at this. The highest power of the numerator here is 3. The degree of the numerator is 3. While if you expand this, this gives you a quadratic equation. So the degree here is 2. Okay, so the denominator degree is 2. So it's an improper fraction because 3 over 2 is improper. Okay. Now, example, let's take an example. So look at this example. Now, let's expand the denominator to check. So x squared plus 3x plus 2. Okay, we've been able to check. The degree of the numerator here is 2. The denominator is also 2, right? So that is an improper fraction. It's an improper fraction. If you do not divide first, you would run into problems. So let's divide. So let's put in the numerator inside the division sign and the denominator outside the division sign. Okay, remember that this is long division. So we ask ourselves, how many times will I get x squared from 2x squared? And the answer there is simply 2. 2 times. So 2 now will be used to multiply everything here. So 2 times x squared gives us 2x squared. 2 times 3x gives us 6x. 2 times 2 gives us 4. The next step here would be to subtract the 2. Subtract this 2. This will cancel out. Now 3x minus 6x will give us minus 3x, and 10 minus 4 will give us 6. So that is our remainder. Now we can express our partial fraction now as 2, which is our quotient, plus minus 3x plus 6, which is our remainder, over x plus 1 into x plus 2. Okay? So that's that for our expression here. So we can now decide to solve the minus 3x plus 6 over x plus 1 into x plus 2. We solve that and we get our answer. Okay? So let's look at this. We can now split this, the minus 3x plus 6 over x plus 1 x plus 2 into, you know, it's linear in the denominator, so we just split it into a over x plus 1 plus b over x plus 2. It's quite easy. Then we can combine the right hand side together. X plus 1 takes out x plus 1, so we have x plus 2 left here. Then b into x plus 1. So then we compare we equate the numerators together. We can decide to use comparing coefficients method here, or we can use the cover up method. Let's use the cover up method. So to find b, we let x be equal to minus 2. This will cancel out a. So substitute minus 2. We have 6 from this. Minus 3 and minus 2 gives us 6. 6 plus 6 equals to minus, this is minus 1, equals to minus b. So minus b is equal to 12. So b equals to minus 12. B equals to minus 12. Now let's also try to get a. So to find a, we'll make x equal to minus 1 so that we can cancel this out. So we substitute minus 1 everywhere where x is. So we have 3 here plus 6 equals to 2 minus 1 is 1, so equals to a. So our a equals to 9. Okay, so if a is 9, we can now put back our answer as 9. Now since b is minus 12, this sign in the middle here changes from plus here to minus. So minus 12, okay? Minus 12 over x plus 2. And that gives us, now we bring back the original equation. So we have 2 plus 9 over x plus 1 minus 12 over x plus 2. We made it. So whenever you see an improper fraction, divide first, then you can now resolve whatever you got as the remainder. Then at the end of the resolution, you bring back the quotient. Okay, so our summary for today is just simple. We talked about repeated factors in the denominator. We talked about what you should do when you have repeated linear factors and how to split repeated non-linear factors. We also now moved to improper fractions and said you should always divide first before you try to split. We also mentioned the new method of direct substitution that you can add to the cover-up method, or to make your work easier and faster. So what I would advise you to do is, I have given you some examples, just some examples on these partial fractions. Find more difficult questions and see if you can actually solve them. Okay, so in that light, I'll show you some questions that you can do for me, and just let me know in the comment section if you were able to get them. Okay, so x squared over x plus 3 all square. Then the second one, x squared plus 2x plus 5 over x plus 1 into x plus 5 all square. Okay, so that is that for our home activity. Try it out. Then if you're able to get this, let me know in the comment section, and practice more questions. So you can also visit quizzes.com and practice some games on partial fractions. It will be fun. So that is our class for today. We're done with partial fractions. So in our next class, we'll be looking at a different topic. It was so much fun. And talking to you guys today was lovely discussing with you. I hope to get some feedback from you on what you need further explanation on, or what you really liked about the topic. Okay, so remember to like the video and share to your friends, and also remember to subscribe for weekly updates. Okay, so I'll see you guys again next week. Have a lovely day. Bye bye.